Hey folks, in this video I'll introduce the sync operation. So again, this is going to be another operation we can use to keep a heap in order. Okay. Previously we talked about swim, and the idea of swim was to take a node that was out of order and move it upwards to where it belonged. Here we'll look at the opposite, right? Sometimes we have maybe a node that's too large and needs to be moved down, right? That'll be our problem, and we'll call that a sync operation. So let's take a look at our tree on the right hand side. Here I have something that's mostly a heap, right? So this looks pretty good, right? This is 7 is larger than 5 and 4. 5, well, here we have a disagreement here, right? My root of this tree, right, which is node 1, is very small. It's 1. It's actually smaller than both 7 and 5, so my max heap property isn't satisfied there, right? So this is a problem. So this is an example where we might want to do a sync operation to move something down to the place it actually belongs. Okay, so let's try. Okay, so let's try tracing this by hand in the example on the screen. So looking over here, right, I know that I'm going to need to start at 1. Okay, so look at 1, and now, unlike swim, I actually have to make a choice here, because I can either go and I can swap 1 with the left, or I can swap it with the right. Right? I have two kind of options there. So which should I swap it with? Take 1 second and think to yourself, would it be better to swap it with that 7, or would it be better to swap it with that 5? Well, hopefully the conclusion you came to is it'd be better to swap with a 7. If I swap with a 5, I'm going to be right back where I started. If I move up 5, then my children will be 7 and 1. 7's less than 5. That means it's out of order with respect to the max heap rule. So I can't do that. In fact, what we want to always do is basically swap it with the greatest child, right? So I have my two choices, 7 and 5, swap with the greatest one, right? So in this case, I'll swap with 7, and so I'll get a 7 over here, a 1 over here, and a 7 over here. So so this is right, a little bit of a work, right? We've made this a little bit better. As a quick note before we move on, one thing about basically doing that swap there is that I know that if I swap the largest of the two children, I won't break the other child, right? So I swapped the largest of 7 and 5, I bring up 7, I know that 7 is going to be larger than 5, right? So what I'm saying there is I'm not going to break the tree by moving up something that is larger, right? It's always going to be a safe operation. It's always going to be larger than the thing that's already there that I'm not touching, right? That 5 on the right-hand side. 7 will be larger because it's already the largest of the children. All right, so this is our first kind of, pass at it. So what do we do next? Now we're looking at this one. And again, we're still out of order, right? So we look at the two children. Two children are larger than our 1. I need to do something about that, right? So I'll use the rule of swap the largest child. Largest child in this case is 5, so I'll swap with that. So this basically goes away. I get my 5 over here and my 1 over here. And at this point, right, I now have a binary, a max binary heap, right? And now everything is in the proper order, right? This last node here, node 1 that I moved down, doesn't have any children, so there's no more places to move it, right? So I'm actually done with it, right? So that's one stopping condition, right? Is if I basically get to the end of my tree. Another stopping condition, right, is also if I'm in the middle and I basically look and I'm larger than the two children. If I'm larger than the two children, then I don't need to move down either, right? So those are my two stopping conditions. Either get to the end of the tree or get to a place where I'm larger than both of my children. Those are my stopping conditions. When I hit either of those, I'll basically be done and I'll produce a brand new, now correct, max binary heap, right, which is what we have here in this picture. Okay, so this is a sync operation. Again, it's for moving things downwards. Let's take a look at the code now, right? This is another example from the textbook if you want to look at it, right, and trace it out, right? Again, they're kind of taking a node and moving it down, right? What we care about here is the source code. So this is sync. So we have here, right, K. K is, again, basically going to be our index, right, of the node that we're moving down. So we have K. Then we have our loop, right? So our loop is going to be the thing that iterates, right, and pushes us down, pushes us down. So the first stopping condition here is, are we at the edge of the tree, right? So 2 times k, basically that's the rule, right, the math rule for getting the left-hand child of a particular node k. So we're asking there is there a left-hand child of this node in the tree, right? If there isn't, what that implies is the node we're looking at is at the very end, right? If there's no place to go, we're at the very end. So no need to go any further. Right, so that's the termination condition for my loop. Have I gotten to the end or not? The next thing I have here over here is basically my selection of my child. Right, so let's say I'm not at the end. I know that I'm in the middle. Right, I'm doing a sync on a node. Right, you picture it in your head. You're doing a sync on a node. You look at the middle point. You're looking at a node somewhere in the middle of the tree. You go and you look at its children. Right, so here, right, you look at J, and you basically pick J to be the left-hand child. Right, so that's what that 2 times k rule means. Right, that's how I go from the node k to its left child. 2 times k. Okay, so I have now basically my J value. All right, so I have my J value. And I basically want to check to see, right, is if I have another better candidate, right? So I have basically a left child of k and a right child of k. So I know it's going to be right next to one another, right? So basically they're at 2 times k or 2 times k plus 1. And so what I'm actually going to do here is I'm going to check to see, oh, am I in bounds? And if I am in bounds, am I actually less than, right? And I, in this case, is basically the child. Is the left child less than the right child, right? That's what that code there is checking. Is j less than j plus 1, right? Is the left child less than the right child? If it is, j plus plus, right? So what we're doing here, right, is basically j starts, right, as this variable is pointing at the left child, and then if the right child is larger, we make it point at the right child. The idea is that j will store the index of the largest child of this node, because that's what we want to swap with, right? We want to swap with the largest child. So this code here is basically determining what is that largest one, right? So I know what my largest child is, and then I can also check, right? So I know where my largest child is, and then I have basically my other stopping condition, which is, am I already in proper order, right? Am I actually greater than my children, right? Am I greater than the greatest children? If I'm greater than my greatest child, that means I can stop, right? There's two negatives here, right? So really it's a greater than, right? So not less than, greater than. So if I'm greater than my greatest child, then I can stop, right? So that's my other stopping condition is over here. So if I'm not greater, right? If I'm out of order, then I do the swap. So I swap with my largest child, and then I update my little pointer to be the child, right? Because in the next loop iteration, I'm going to want to look at that child and potentially move them downwards. All right, and so this, of course, is a while loop, and so it repeats until you get to that end of the tree or get it to the proper position. All right, so that's it for the swing operation. Again, we're not going to use this directly, but rather we're going to use it inside of our priority queue to implement some of the functions.